Welcome back. In our previous video, we introduced the concept of a transformer, a type of neural network architecture that's central to many of today's most impressive AI tools. In this video, we're going to use that information to explore something bigger, large language models, or LLMs, powerful systems that expand on transformers to process and generate text in remarkable ways. Let's start with a quick recap of the transformer idea. Recall how transformers process entire sequences of text in parallel, rather than just word at a time. Instead of reading text like a person reads a book from left to right, a transformer soaks in all the words together. The key operation inside is called attention. Attention helps the model figure out how each word relates to other words in the entire sequence, adjusting each word's internal representation accordingly. With that in mind, we can see how a language model, especially a large one, boils down to predicting what comes next, word by word, or more precisely, token by token. If we feed it a passage like, once upon a time, there was a brave, the model's job is to figure out which word most likely follows. Then it moves on to the next and the next, generating a flow of text one piece at a time. Now, you might be thinking, really? All it does is guess the next word? How could that possibly generate a conversation or solve problems? Well, it turns out that by learning to predict the next word on huge amounts of data from all over the internet, think billions, even trillions of words, the model internalizes an enormous amount of statistical knowledge about language, and even knowledge about the world. Because such models generate new tokens, instead of performing some classical AI tasks like classifying digits, we call them generative AI. But raw next word prediction alone doesn't necessarily make it conversational or task oriented. If you only do that pre training step, you'll end up with a model that can generate plausible text, but might not know how to politely answer your question or follow your specific instructions. This is where fine tuning comes in. For example, we can gather lots of conversation logs or question answer pairs, often with human feedback included. We use these to adjust the model's parameters so that it becomes more aligned with human dialogue. This phase might involve techniques like reinforcement learning from feedback. In this technique, people rank or correct the model's responses, nudging it to respond more helpfully, avoid harmful content, or follow certain stylistic guidelines. During this process, the model is still predicting words, but now the data it's trained on explicitly demonstrates how to follow instructions or hold a chat like interaction. Imagine a specialized scenario. You have a huge transformer that's learned standard language patterns. Then, you give it extra examples like, how do I bake a chocolate cake? Followed by a well structured, helpful answer. The model adjusts so that whenever it sees a prompt resembling a user question, it becomes more likely to produce a helpful, step by step response. That's fine tuning. It sculpts the raw next word predictor into a more functional assistant. Now, the next big question. If we're talking to a chatbot, how does it remember what we just said? After all, a large language model doesn't have a spinning disk or permanent memory system storing your entire conversation. It's actually stateless. Once it's done producing a response, it isn't literally storing that chat history inside itself the way we humans store memories. So, how does it keep track of the conversation? The answer is the context window. You can think of the context window like a short term memory buffer the model uses for each round of prediction. Whenever you type a message, your input, plus any relevant past conversation text, gets packed into a window of tokens. The model then sees everything in that window all at once when generating its next response. That's how the model knows, the user just asked me a follow up question about chocolate cakes, so I need to keep talking about recipes. But keep in mind, the context window has a fixed and finite capacity, even though it might go up to millions of tokens. If your conversation is too long and spills beyond that capacity, other parts of your dialogue will drop off. The model literally can't see them anymore. It's like having a short term memory that can only hold so much information. So, if the conversation keeps going and on the 50th message the user references another, older message that's now fallen out of the context window, the model has no direct memory of it. The model is stateless and only uses what's present in the current window. If the original mention of that detail is no longer in that window, it just can't rely on it. The user must reintroduce it in the new prompt so it's back inside the text the model sees. So, you might ask, if the model is stateless, how do we keep track of a continuing storyline or complex instructions that build up over time? The short answer is that the software wrapping the model must keep resending the relevant text in the conversation so it appears in that context window each time. The model is unbelievably good at pattern matching across that text in that context window, but it's all thanks to that repeated feed of conversation text. It's not storing it internally like a database entry. This is why, in many applications, carefully managing what text you include in the prompt is so crucial. In more advanced cases, that we will cover in the next module, you might see systems that dynamically fetch all their messages from a database or knowledge store and inject them into the context. They are effectively giving you a way to emulate longer or more persistent memory. In the next video, we'll talk more about large multimodal models. Welcome back. So far, we've talked a lot about large language models, the types of AI that take in and produce just text. But here's a fascinating fact. The transformer architecture and other similar designs don't have to stop at words. In the real world, information comes from many modalities. We have audio, images, video, even data from sensors like depth cameras. And just as we can tokenize text and create embeddings for it, we can do the same for all these other forms of data. We can treat everything as language. Training AI on all of these modalities creates a multimodal model, an AI capable of processing, interpreting, and generating outputs across various input types. Training such a system is no trivial task. It demands large, high-quality datasets that pair each modality with meaningful annotations or corresponding information. If you want your model to understand images and captions, you need a dataset of images matched with descriptive text. For speech recognition, you need voice recordings aligned with transcripts. During training, the model learns to correlate the structure of one modality with another, so it can fuse multiple data streams in more complex tasks. The possibilities are immense. A multimodal model can look at a screen and describe it in words. It can listen to audio and generate a text transcription or translation. It can interpret both video and sound to detect events in real time. Beyond these straightforward tasks, we can push it into more creative realms. You might provide an image of your living room along with a prompt like, propose a minimalist makeover, and the model could produce a redesigned layout. By handling multiple input types at once, the AI can capture context that a single modality system would miss. Of course, multimodal training introduces new challenges. Gathering the right data is a hurdle. Good multimodal datasets are expensive to curate and label. Another difficulty is the sheer computational load. Processing entire video sequences or high fidelity audio requires more memory and more advanced hardware than text alone. Models must also learn how to blend the different modalities without getting overwhelmed by noise or inconsistencies. There's a risk of spurious correlations if the data isn't balanced or representative, which can lead to bizarre or biased outputs. To wrap up, multimodal models expand AI scope beyond text, letting it process and generate images, audio, and videos along written words. Attention-based architectures still drive the learning. The trick lies in encoding and aligning diverse data so that the model can discern meaningful patterns. In the next video, we'll see how a different type of generative AI is used to create new images and videos. Imagine you have a photograph of a coffee on a wooden table. Now, picture taking that beautiful image and adding a little bit of random noise, tiny dots and static that start to obscure the details. If you keep adding noise over and over again, eventually the photo becomes unrecognizable, just like a field of static noise. Diffusion models work by learning how to reverse that process. It's like teaching an artist to look at a static field canvas and patiently uncover the hidden picture underneath, step by step. This is very different from how transformers operate. Transformers soak in entire sequences at once, then spit out the next token. They're brilliant at tasks like language generation or even image captioning. But in a diffusion model, you're not stepping forward in text or data sequences. Instead, we step backwards in time, reversing noise. So, why were diffusion models built in the first place? Think about the goal of creating entirely new images. For a while, to produce novel images, researchers tried approaches like generative adversarial networks. They could do some amazing things, but also had their quirks, sometimes missing diversity or being tricky to train. Diffusion offered a fresh perspective. By literally taking a real image, slowly corrupting it with noise, and teaching a neural network to remove that noise, you end up with a model that learns how images are formed from randomness to crisp pictures. Once it's trained, you can feed in pure noise and the model gradually denoises it into a completely new image that's never existed before. And you can apply a text prompt to guide this denoising process. For instance, let's say we want a picture of a landscape of a serene lake. The diffusion model will start with a cloud of random noise and, across many steps, refine that noise into a crisp image of exactly that scene. Now, as soon as people realized how powerful these diffusion models were for images, we naturally began to wonder if we could do the same for moving images too. Could we diffuse noise into a video? Imagine each frame in the video having noise added until you can't distinguish anything. Then, you train a model to remove that noise in each frame while keeping consistency over time. So the concept is the same, but with videos, there is a whole extra dimension: time. It's like instead of a single picture that needs to be reconstructed, you've got to piece together an entire story of frames that blend seamlessly into one another. That means the model not only has to restore each individual frame, but also has to learn how frames connect. The model needs to capture how things move and interact in realistic ways. A galloping horse must keep the right pace, objects should obey gravity, and shadows should stay consistent. Without an internal notion of physics or real world behavior, the resulting video could look strange. For instance, objects might warp or drift erratically, shattering the illusion of reality. So, to recap the big picture, a diffusion model takes data, an image or a frame in a video, and it learns the opposite of adding noise. That's different from a transformer, which usually tries to model sequences directly, predicting the next chunk of data. Diffusion is about taking random, chaotic input and systematically sculpting it into something meaningful. In practice, that training requires a lot of examples. Real images or real videos are used to figure out how noise typically corrupts them and how best to remove it. Once it's trained, this same process of removing noise becomes a creative tool that can generate a kaleidoscope of possibilities from plain, random input. That's how we get new images and videos. Imagine you're reading a detective novel where the main character uses meticulous step by step reasoning to solve the case. In the previous video, we explored how large language models can generate coherent answers by predicting one word after another. But there's a fascinating twist to how we can interact with these models. We can encourage them to show their train of thought, like the detective spelling out each clue as they piece it together. And this is called chain of thought prompting. Chain of thought prompting means that instead of asking the model to jump straight to the final answer, we explicitly ask it to reason out loud, step by step. You might say something like, "Explain your reasoning here," or "Please walk me through how you got that conclusion." Because the model has so much built in knowledge, it can follow those instructions surprisingly well. To see why this works, think of the model as a puzzle solver that's already packed with puzzle solving techniques, gleaned from its massive training. If you just ask for the solution, it will give you an answer. But if you also say, "Show me your work," it's more likely to unroll the thought process that leads to that answer. That unrolling can, in many cases, correct potential missteps and produce a more reliable conclusion. This can be illustrated with something like a mini logic puzzle. Alice is older than Bob, Bob is older than Carol. David is younger than Alice, but older than Carol. Eve is younger than Bob, but older than Carol. Who is the oldest and who is the youngest? Instead of giving a one word answer, the chain of thought approach prompts it to lay out the reasoning. You can practically see the logic playing out. If you look closely, this idea of guiding the model to reveal its step by step logic starts to resemble a form of automation. Once you know that the model can reason through a series of steps, you can design prompts that direct how it thinks for a wide variety of tasks, like, for example, programming. If you design the prompts well enough, the model might reliably go through the steps to produce useful answers. Maybe your prompt is to solve a math problem, to craft a plan for your next big project, or to analyze a complicated text and summarize it. Each time, the model can demonstrate its work, showing each decision and each link in the chain. It's not just about the final answer anymore. Instead, it's more like programming a chain of instructions. When you see it spelled out in the model's step by step chain of thought, it feels like a script being executed behind the scenes. You get to watch it happen in real time, and this opens up possibilities for verification and control. For example, if one of the reasoning steps is flawed, you can spot it and correct it, rather than having to guess where the final answer might have gone wrong. What's truly wild is that this chain of thought style can help unlock deeper capabilities that might not surface otherwise. Sometimes, a model that struggles with complex math problem in answer-only mode will get it right if you explicitly ask it to detail its reasoning. It's almost like tapping into the knowledge the model already has, but in a more methodical, systematic way. Sometimes, you solve problems seemingly on autopilot, and at others, you painstakingly walk through each step. It's almost like talking to yourself in your head. In a way, large language models have these two modes of thinking as well. One mode is when the model immediately provides an answer, which we can compare to our unconscious or System 1 thinking. It is fast, intuitive, and often hidden beneath the surface. Another mode is when we explicitly prompt the model to show its chain of thought, effectively inviting a more deliberate, System 2 style of reasoning. This one is slower, step by step, and easier to inspect. This dual nature has a deep parallel with how humans think. System 1 is the constant stream of subconscious pattern matching that lets us understand language, react to stimuli, and recognize faces without slowing down. System 2, on the other hand, is that conscious, methodical thought process that we engage for tougher or novel problems. Good examples are doing math or planning a project. By telling a language model to show the reasoning steps, we shift it more into a System 2 space, revealing its hidden or latent capabilities. Of course, none of this is exactly how the human brain works, but the analogy is useful for understanding some of the emergent behaviors of these models. Just like humans can choose where to rely on quick intuition versus careful analysis, we can choose whether the model should simply produce an answer or outline a detailed chain of thought. This choice can lead to more transparency and often to better outcomes in tasks that benefit from explicit reasoning. Now let's step back and look at the machinery under the hood. In the context of AI, you might have heard GPUs being mentioned a lot, so let's clarify what they are. A GPU is a graphics processing unit, originally designed to handle the heavy computation of rendering images and animations in video games. But their ability to process many operations in parallel makes them perfect for large-scale machine learning tasks. Instead of single processor crunching numbers one at a time, GPUs can handle thousands or even tens of thousands of these calculations simultaneously. When we train a large language model, we talk about train time compute, the massive amount of calculations needed to adjust the model's parameters from random guesses to something that accurately reflects pattern in the training data. Here, GPUs are vital because training involves running vast amounts of data through the model and fine-tuning billions of parameters. As you might remember, these are essentially the model's dials and knobs that get set to capture patterns in language. By comparison, test time compute, also called inference, is the computational workload needed whenever we want the model to generate outputs, like answering questions or producing chain of thought. At test time, we no longer adjust the model's weights. The model is already trained. Instead, we're just asking the model to think longer and harder, sometimes providing many, many elaborate chains of thought. Even though it's a smaller burden than training, inference can still be significant for very large models. Hence, GPUs are still extremely helpful to churn through all these calculations quickly. Another important term is so called scaling laws, which are empirical rules about how models tend to get better as you ramp up the size of the model, the amount of data, the compute power, or how much time we give the model to think. Different scaling laws exist for train time compute and test time compute, and the two are fundamentally different paradigms. So, training is that heavy, one time investment, the phase that shapes the deep patterns of knowledge that model holds. Inference, or test time, is when you tap into those learned patterns, either to get a quick, intuitive like answer or to watch it reason step by step. Both of these resemble, but are not identical to, how humans think. In both phases, GPU power fuels the underlying math. During training, it's used to iteratively adjust parameters. During inference, it's used to effectively serve the predictions and chains of thought. Now, you might be wondering how these models get better with test time compute. After all, if the model starts off pretty clueless about something, no amount of additional time to think will make it magically smarter, right? Well, that depends on how we approach the problem. That's where reinforcement learning comes in. Reinforcement learning is about training agent to take better steps over time, whether it's a robot navigating an environment or a language model searching for the right answer. It works by rewarding the agent for good outcomes and penalizing it for mistakes, shaping its future behavior. In the case of language models, this is how we fine tune them to transition from simple text generation to holding meaningful conversations. It turns out we can apply the same reinforcement learning principles with chains of thought. With more test time compute, the model can generate many different chains of thought, essentially trying different paths to solve a problem, like for example a coding or a research problem. Most will lead nowhere, but some will inevitably be valuable. A separate model can step in to identify the high quality answers and reward the original model for producing them. Over time, these rewards guide the model to prioritize better reasoning paths in the future. It's like training a pet to perform a trick. Every time it gets it right, you reward it, reinforcing the behavior until it becomes second nature. This can make the model surprisingly good at tasks where there is a well defined right answer, like certain scientific or factual questions. It's because the correct chain of reasoning is pretty straightforward to identify and reward. However, this method can still stumble on less well defined situations, like common sense reasoning or social understanding, where the lines between correct and incorrect are blurry. Humans themselves sometimes struggle with common sense, let alone a machine that relies on patterns in data and signals from reinforcement learning. So, while scaling laws and reinforcement learning are powerful tools for pushing these models to astonishing levels of performance, we need to remember that even the largest, most well trained models can miss the mark on more intuitive, everyday reasoning.